Now that we have a function, the principal value of the complex logarithm, we ideally should have an inverse relationship between the exponential function and the log function. Now, unfortunately, it's a little bit more complicated than what happens for real numbers. So, so let's go over that. So let me recall for you that the exponential function e to the z is 2 pi I periodic. And what that told us was if we were to sort of chop up c into 2 pi I pieces, so here's a pi I, and here's down here at negative pi I, and then here's up here at 3 pi I, and here's down here at negative 3 pi I. Every slab of every horizontal slab of width 2 pi, the exponential function repeats the output. So in particular, what this tells us is that since it's 2 pi I periodic, it's not one-to-one everywhere. So we shouldn't expect we should not expect something like log e to the z is z for all z. It's not something we should expect because the exponential function isn't one-to-one, so there could be multiple z's that have the same e to the z, and the log function wouldn't know what to do with that. While it is true that when you do this other direction, you do get z, provided it makes sense to plug it into log. But we shouldn't expect this first guy. That guy is not necessarily going to be true. So what we need to do is we restrict the domain for the exponential. So to fix this, we're going to restrict the domain of the exponential function to the set. We want to do one of two things usually. We want to include this upper boundary of the fundamental region, this solid upper line at imaginary part is pi I. And then in some cases, when we want to be able to differentiate the log function, we're gonna remove it. But I'm gonna say the biggest possible set. So we want to restrict the domain of e to the z to the z's such that the imaginary part of z does not exceed pi I. So that's this upper bar, and it does exceed negative pi I strictly, and that's that lower bar. Or if we wrote this in terms of x and y's, sort of the x plus I y's, where x can be anything, and y's are stuck between negative pi and pi, inclusive at pi. Means the same thing. So once we do make that restriction, then it is the case that the exponential function is one-to-one, and the logarithm function is the inverse. So this means two things. Well, it means that the log of e to the z is z for all z. Let's call this d for the domain for all z and d. Let's not use d. Let's call this r. D is often used for an honest domain, which is an open set. This is not open because it's closed off on that upper portion. And e to the log z is also z. And this is for all z not 0. Okay? So when we do this, now we have an honest function, and it's an honest. It has an inverse once it's a not an honest function. We have a one-to-one function, and it has an inverse now.